A warm welcome. This is Control Systems course with the lecture 1.4 representing DC and AC servo motors. A servo motor, normally a servo, the word represents the position. So the servo motor is nothing but we are finding out the position of the motor. In the sense, the rotor position is sensed. So we are sensing the position of the rotor, and then that will be provided as a feedback to any control system, and finally the motor will be made to operate efficiently. So this is what is the process which is carried out called the servo mechanism in these DC and AC servo motors. Let us see about servo motor of AC type first. So AC servo motor is essentially a two-phase induction motor with modified constructional features of the normal servo motors. So we have the schematic diagram of the two-phase or servo mechanism. Here we have the actuation signal which is being provided to the servo amplifier and which is then fed to the control winding. Here we are having the value as V0, the voltage. And the rotor, the second phase is being the reference winding where the voltage applied is called VR, that's the reference voltage. So while comparing the reference voltage and the actual value V0, the rotor is made to operate accordingly, and here we represent theta, J and V0 as the elements here. The two-phase servo motor, it has two windings displaced by 90 degrees on the stator. One winding is called reference winding and is supplied with a constant sinusoidal voltage. The second winding is called a control winding, which is then supplied with the variable control voltage, which is displaced by 90 degrees out of phase from the reference voltage. The major difference between the normal induction motor and an AC servo motor are the rotor winding of an AC servo motor has high resistance when compared to the inductive resistance, so that its X by R ratio will be very low. For a normal induction motor, the X by R ratio is high, so that the maximum torque is obtained in normal operating region, which is around 5% of the slip value. The torque speed characteristics of the normal induction motor and that of the AC servo motor are represented here. We can see in case of AC servo motor, the torque speed characteristics is a straight line, while in case of normal induction motor, since X by R value is very large, the torque value will be very high for even the small speed, and after a limit, it may get reduced to zero when synchronous speed is reached. The torque speed characteristics of the normal induction motor is highly non-linear and has a positive slope. It is not desirable for control applications that the positive slope makes the system unstable. The torque speed characteristic of an AC servo motor is fairly linear and it has a negative slope throughout. The rotor construction is normally squirrel cage or drag cup type for the AC servo motor. Here the diameter is small when compared to the length of the rotor, and this will be reducing the inertia of the moving parts. So the acceleration characteristic will be very good, and finally the dynamic response will also be very good. The supplies here of the two windings are not balanced as in case of the normal induction motor. The control voltage varies both in magnitude and phase with respect to the constant reference value. So, which is applied to the reference winding. Hence, the direction of the rotation of the motor will depend upon the phase, that is plus or minus 90 degree of the control voltage with respect to the reference voltage. For different RMS value, the diagram is being represented. Here, the E3 value will be the maximum voltage, while E0 value will be the minimum voltage. So we can see the torque speed characteristics differences. The torque varies approximately linear with respect to speed, and also based upon the control voltage value. The torque speed characteristics can be linearized at the operating point, that's the Q point, and the transfer function of the motor can be obtained at that point. Next is DC servo motor. Normally, AC servo motor and DC servo motor differences are considerably valid when we normally compare the AC motors like induction motor or synchronous motor with the DC motors. So similar representations will be there. The DC servo motor will be can be have it has the characteristics of DC motors as well. The DC servo motor is actually an it will be active with a load and is usually a DC motor of low power rating. The DC servo motors have a high ratio of torque to inertia and therefore it will be having a faster dynamic response. The DC motors normally are constructed using the rare earth permanent magnets which have high residual flux density and high coercivity. As no field winding is used, the field copper losses are also zero and hence the overall efficiency of the motor is very high. The torque speed characteristics of this motor is flat over a wide range as the armature reaction is negligible. Moreover, the speed is indirectly proportional to the moreover speed is directly proportional to the armature voltage for a given torque. The armature of a DC servo motor is specially designed to have low inertia value, and in some applications the DC servo motors are used with magnetic flux produced by field winding. I mean this electrical system combined with the mechanical or coupled with mechanical system can using these equations. So the Tm value is nothing but the representation of the armature current. So it is Kt into Ia. Kt is nothing but a constant, and the back EM of Eb is equal to Kb, a constant value into omega. And here we have the electrical system as per the mesh equation, and here we have the normal mechanical rotational system equation. And on applying the Laplace transform, we can transfer the system as such. We have to find out the transfer function, I mean the angular velocity divided by the applied armature voltage. On substitution, we get the final equation as omega of s by A of s is equal to Km divided by tau m s plus 1, where Km represents the constant values and parametric values, and tau m it's nothing but the motor time constant, and this will be normally when designing a DC servo motor with the help of a transfer function, this time constant is being given more importance. While varying the time constant, how the motor representation will be there. So this is how the scientific studies are being applied. And next, while considering the field controlled DC motor, here we are applying the field current, which is a variable one. And here we can see the diagram as EF, the input voltage. Here the armature voltage will be constant, that's all. Here IF, the field current, and then we have RF resistance, LF inductance. Similar, it is coupled to a mechanical system. And this is how we will be framing the equations of the system represented. So actually, while comparing the armature controlled system, there we have back EMF effect since armature voltage is applied. But in case of field controlled system, the back EMF value, I mean the back EMF impact will be negligible. So we are avoiding that equation, and so we have only three equations. On applying these Laplace transform for these three equations, we get the equations get transformed into this state, and finally we can obtain the output as there we have theta of s by E of s. It's nothing but the output theta of s divided by the applied voltage EF of s. This is how we will be getting the equation. Here we have three different constants. One is Km, one is tau 1, and other is tau f. That is a field time constant. So we have motor gain constant, motor time constant, and motor field effect. Field time constant.